Hello guys, Dr. Hasbullah here, and in today's video we're going to be looking at a couple of questions, a couple of tutorials, so you understand very well how to use the equations that we've derived before. Now let's move to the first question. Okay, now imagine if you have a reservoir, okay, and then at the exit of the reservoir you have a nozzle, right? And then you have something that is called the receiver. So this is receiver. This is reservoir. Okay, and this reservoir has a few properties. So temperature here is 20 degrees Celsius and the pressure here is 500 kilopascal. And the flow is obviously flowing from left to right. And what we need to find now is the mass flow rate. Okay, under two conditions. Okay, what is the mass flow rate if A, the receiver pressure, the absolute pressure inside the receiver, okay, so this is PR. What is the mass flow rate if the absolute pressure at the receiver is, first is 300 kilopascal, and what would be the flow rate if the absolute pressure at the receiver is 200 kilopascal, right? And I also want to show you different methods of solving this problem. First is that we're going to use our equations. And the second is we are going to use what we call isentropic flow table. When you are presented with this kind of question, what should be your first priorities? First of all, you need to know whether the flow is subsonic or supersonic. Okay, when it enters the receiver, given the pressure of the receiver, either 300 kilopascal or 200 kilopascal, did the flow goes to Mach number 1? The reason why this is important is because you are looking for the mass flow rate. When Mach number equal to 1, then the mass flow is maximum. The mass flow cannot be larger than what it is when the Mach number is equal to 1. And this phenomena is called choking. As long as the Mach number is equal to 1, it doesn't matter if you increase the pressure difference, right? The mass flow will remain constant. And that is very important to determine. Okay, so let's see at what pressure the mass flow will choke. And at Mach number equal to 1, we know that we already have the relationship of pressure before. Okay, let me show you. Right, I think this is the relationship. Okay, so when P star equal to 0.5283 P naught, which is the pressure inside the reservoir, then the Mach number is equal to 1, which means the flow is choking. Now, let's see what is the P star. Okay, so P star over P naught is equal to 0.5283, right? So that gives us P star equal to 0.5283 times the pressure in the reservoir, which is 500 kilopascal. Okay, and you will end up with 264.2 kilopascal. Okay, and what is this pressure? And this is the pressure inside the receiver if you have Mach number equal to 1, right? So obviously, let's take a look at our two cases, right? So we know now that for case A, the pressure is 300 kilopascal, okay? So the pressure difference between the reservoir and the receiver is not large enough that Mach number equal to 1, right? So basically, this is saying that in this case, Mach number is less than 1, right? And in this case, for case B, this case, Mach number is 1. Alright, Mach number cannot be greater than 1 because this is a converging nozzle and the area is only getting smaller and smaller, right? So it cannot go supersonic. So question A is where our pressure in the receiver is equal to 300 kilopascal. Right, let's take a look at what are the equations that we can use in order to solve this equation. And I think we can use this equation, right? So P naught over P is equal to 1 plus K minus 1 over 2M square. Let's take a look at the power. Okay, this will be K over K minus 1. Right, and our objective now is to find what is the Mach number, because using this Mach number we can find the mass flow rate. So P naught is 500 and P is 300. equal to 1 plus k, let's assume 1.4 minus 1 over 2. That's the normal k that we use. This is m square 1.4 over 0.4. So your m would be, now even before we calculate m, we know that m has to be less than 1. So this is 500 divided by 300 to the power of 0.4 divided by 1.4 minus 1 times 2 divided by 0.4 squared. This is 0.8864. This agrees with our initial observation, which is m should be less than 1. The flow is still subsonic. Now, when we have the Mach number, we can always find the equations to find whatever we want. Okay. Now we want to find the mass flow rate. Okay. Let's take a look at the equations that we've derived before, and I think this equation would be suitable. Okay. This equation. Let me highlight it for you in green. Okay. So this equation seems suitable because we know everything. We know P0, we know K, we know R, we know T0, we know area. Now we have the Mach number and we have K. Okay, so that's all we need. Okay, and when we use this equation, okay, I'm just going to write it back to you here. M dot is equal to P0 square root of K R T0 times Mach number times area multiply with 1 plus K minus 1 over 2m square, and this is K plus 1 over 2, 1 minus K. Now what's left is just to plug in the numbers. And P0 we know is 500,000 Pascal. Square root of K is 1.4. R is 287 times T0 is 20 degrees Celsius. So this is 20 plus 273. Always make sure that it is in Kelvin. Okay. Multiply with our Mach number is 0.8864 times the area, and our area is, then I forgot to mention the area. Okay. And the area here is 0.001 meter square. Okay. So this is our area. 0.001 multiply with 1 plus 1.4 minus 1 divided by 2 m square. This is 0.8864 square to the power of 1.4 plus 1 over 2 times 1 minus 1.4. Now obviously this is a very long equations, and I need you to be careful when you put these values into your calculator, right? And in the end you will end up with 1.167 kilogram per second. Okay, so that's your m dot for case A, right? And for case B, we know that the pressure inside the receiver is 300 kilopascal, and we know that in here Mach number is equal to 1. So now we're going to use Mach number 1 and put in the equations that we did just now. And when we know the Mach number is equal to 1, let's go back to our equation here. Right? And now we can use this equation, right? And obviously this is just the previous equation, but with m equal to 1. Okay, so it simplifies like this. And our m dot becomes P0 K over R T0 times A star multiply with 1 plus K minus 1 over 2 m square K plus 1 over 2 1 minus K. Let's key in together all the values that we know. This is 500,000. Square root of K is 1.4, R is 287, times T is 20 plus 273. A star is 0.001 multiply with 1 plus 1.4 minus 1 over 2 m square. Sorry, now m is 1, sorry about that. 1.4 plus 1 over 2, 1 minus 1.4. And in this equation, you will end up with m dot equal to 1.181 kilogram per second. Right, and relatively, when you compare these two values, okay, it's kind of makes sense, right? Because at Mach number equal to 1, then the mass flow would be slightly higher than Mach number less than 1. The important point that I want to show you inside this tutorial is how to use the isentropic flow table. If we do it correctly, we should be able to get similar value either using equation or using the tables. Now we go back to question 1, which is PR equal to 300 kilopascal, right? And when we know that the pressure is 300 kilopascal, what we need now is the Mach number, right? And I can tell you that, and we know that PO is 500 kilopascal. So basically, PR divided by PO is 300 divided by 500. So that gives you 0.6. Now let me show you what the isentropic flow table looks like. Depending on your reference, for example, I'm using Porter Introduction to Fluid Mechanics book, and this is what I find in the appendix of this book. And if you don't have textbook, just Google isentropic flow table, okay, and you will get this table. So this table usually consists of the Mach number, alright, and then the pressure ratio, temperature ratio, and area ratio. Okay, and what we have just now is that P over P naught is 0.6. So that is where we are going to look at. So 0.6 is between these two. Okay, and what we are looking for is the Mach number, right? And Mach number should be between 0.88 and 0.9. Okay, now what you need to do is the usual interpolation method. So what I'll do is I'm going to copy these values, so we don't have to go back and forth. Okay, so these are the values. And now what we need is the Mach number. So our Mach number minus 0.88 over 0.9 minus 0.88 is equal to our pressure ratio, which is 0.6 minus 0.6041 divided by 0.5913 minus 0.6041. Okay, and let's see what is our Mach number. 6 minus 0.6041 divided by 0.5913 minus 0.6041 times 0.02 plus 0.88. So this ends up with 0.8864. Okay, let's see, does it match with the way we did using the equation? Right, so exactly. Okay, so now you can see clearly that you can either use the table or you can use the equation. It's up to you. We know that the third row is the temperature ratio and the fourth row is the area ratio. Okay, and remember what we need before? We need the temperature, right? So temperature is the third row, so it will be this one. And again, we're going to need to interpolate to find the temperature ratio. And let's say our T divided by T naught is equal to X, for example. And now we want to interpolate. So X minus 0.8659 over 0.8606 minus 0.8659. And I'm going to use 0.6 minus 0.6041 over 0.5913 minus 0.6041. Okay, and I'll get X equal to 0.864. Okay, so this is also T over T naught. So basically T, which is also is T at the exit of the nozzle, is equal to 0.864 times T naught. Right, and my T naught is, if you remember, is 20 degree plus 273. You will have 253.15 Kelvin. And to find the mass flow, let's go back to the original continuity equation, which is rho times velocity times area. We already know area, right? 0.001. Now, what is rho? According to the ideal gas equation, P equal to rho times R times T. So, rho is equal to P over RT. Okay, so immediately we're going to replace that. This is P over RT. What is velocity? Okay, Mach number equal to velocity divided by speed of sound. So, velocity is Mach number times speed of sound. But speed of sound is m square root of kRT. Right? I'm going to replace it here. This is m square root of kRT. And area is 0.001 meter square. And if I plug in all the equations, and now we have P. P is 300 kilopascal, so that's 300,000 pascal, divided by RT. R is 287. T, our new T is 253.15. And I may run out of space, so multiply with my Mach number is 0.8864. Multiply with square root of 1.4 times 287 times 253.15 times my area is 0.001. Okay, and my mass flow rate becomes divided by, so this is 300,000 divided by 287 divided by 253.15. This is 4.129 times 1.4 times 287 times 253.15 square root times 0.8864. This is 282.7 times 0.001, and you will end up with 4.129 times 282.7 times 0.001. This is 1.167 kilogram per second. Okay, and let's compare this with our mass flow rate using the equation. Okay, this is 1.167 kilogram per second as well. So exactly. And we have one more case, which is case B, where the pressure at the receiver is 200 kilopascal. And in here, we already know that M equal to 1 at this location. So at M equal to 1, these are the parameters. So from the table, we know that P over P naught is equal to 0.5283 and T over T naught is equal to 0.8333. Okay, so that's quite simple now. So when we need the pressure is 0.5283 times 500 kilopascal. This will be 0.5283 times 500, 264.15 kilopascal, and the temperature is 0.8333 times 20 plus 273, and this becomes 244.16 Kelvin. And again, to find the mass flow rate, again, we're gonna use this equation. Okay, I'm just gonna copy this. Okay, if I can copy this, put it here. Okay, and our pressure now is 264,150 over R is 287, T is 244.16 times M is 1 times square root of 1.4 times 287 times 244.16 times area is 0.001, and the M dot that you get is 264,150 divided by 27 divided by 244.16, 377 multiplied with 1.4 times 287 times 244.16 times 0.001 square root, 1.4 times 287 times 244.16 square root. This is 313.2 times 0.001, which is equal to 1.181 kilogram per second. And let's compare that with what we have before using the equation, and exactly 1.181 kilogram per second. So the result is exactly similar whether you use the equation or you use the table. Because essentially when they develop this table, they use the same equation. Just plug in the K and also the Mach number. So I think this video is getting a bit longer. Okay, so we stop here now, and in the next video, I'm going to show you the second example. Thank you for listening and see you soon. Bye.